Okay, good morning, how are you doing? So my name is Mark Scanlon. I've been speaking to some of you guys already. I'm from University College Dublin. This work was primarily conducted by Taj Ahwal, who had intended to come and present to you, but at the last minute had to cancel his plans. Taj was a student of ours in UCD on our master's programme who graduated last year, and this is a paper that has been produced as a result of his dissertation research as part of his master's. It's co-authored by myself and my colleague in UCD, Anne Lecac, who supervised the project. So, the main points that I'm going to cover here is to go through exactly what Spotlight is, if you're not familiar with it. Those of you who are using Macs, I see a lot of Macs in the room, will be very familiar with it, I imagine. Talk through how we designed the experimentation, what was conducted and what we found, go through some of the results of what we had, and then I'm going to tell you what I told you again. Okay. So, first of all, Spotlight looks like this. It's a Mac desktop search utility. So it started in 2004. It was released by Apple. And it was purely desktop search. So when it was released initially, it indexed the files on your local disk and allowed you to search those files relatively easily. It's evolved over the years with the releases of Mac over the years as well. So now it does things like preferring some online searches as well. So you can see here, even in this example, it's doing an online search for a dictionary lookup or for related websites or apps in the App Store, stuff like that. But the stuff that we're interested in is that it indexes the files on your local disk and allows you to search through those files. So on the left-hand side, you get the results for whatever you search for. On the right-hand side here, you can get a thumbnail, perhaps, of what that image looks like, of what that movie might look like, what that document looks like. Okay? So if you think about when this was released, it was released in 2004 for the first time. Internet search was already popular, so that was started by Alta Vista back in 1995 or so. So if you think about web search, while it's not trivial, it's easier than looking at proprietary formats on a desktop machine. So web search, it's a text-based search. There's a standard, so the HTML standard is there. We know what we're looking for when we look through such a formatted document. So web search and indexing is relatively straightforward. Trying to build an index and to actually look inside of proprietary formats on a desktop search is more complex. So it was released in 2004. It allows you to search for information using keywords. And of course, Spotlight creates databases. So it stores everything from the file system attributes, metadata, and it actually indexes any of the textual content that it can discover in a file. For those of you who are not Mac users, if you've ever shared data with somebody via USB key and you get all those extra .spotlight files and .fs events files that annoys everybody, they're the files that are used for indexing each device. Okay, so I'm speaking on Taj's behalf, as I mentioned. So he had this interest in this subject since 2011. So the reason that he focused on this for his research topic on his master's was that the number of Macs that he was encountering in his lab was increasing. The popularity of Macs is obviously continuing to grow. So in 2011, he started off looking at keyword hits on Spotlight directories. There were no tools available to parse the data. The format of the databases was proprietary and not documented. There was no published research about what that looks like from Apple or anyone else. In 2013, a company called 50 Forensics, you see what they did there, they announced a tool called Spotlight Inspector, and they had built a tool and they had reverse engineered the format, but the tool disappeared almost immediately as it was released, and the structure was not revealed, it wasn't made open source, and it's not available any longer. It's based on the documentation that we can find about that tool, it was not known if it had any capability to handle deleted records in any way. So in 2016, when he started his master's, the examining of Spotlight had not really progressed. So the current best practice for looking at this stuff is to use a lab machine, a VM or something. You mount the device that you're looking for. So every single hard drive or storage media in the root of that device will have these Spotlight databases. And you use the official Apple tools, the command line tools that Apple provides, to interrogate that database. So you're kind of manually looking through these records, and none of those methodologies that are there so far offer a solution for recovering deleted records. So to give you an idea what this might look like, this is just a small sample bash script. I should say this script and more is available on a GitHub, which I'll have a link on the last slide for you guys if you want. So the line that really matters is that you're looking through the file, you're looking through the content for any of these database files, and the one that really matters to you guys here is this line here, 104. So line 104 here, you're calling on MDLS, which is the Metadata Lookup Service. That's what that stands for. And you pass it in some parameters, and it'll look up to see if there's any records for this file already in the store, and it'll return those metadata records back to you. That only works for currently active files, currently existing files, not for deleted files. Okay, so metadata is obviously a hot topic within forensics. The more metadata we can get our hands on, the better. To make the most of the metadata, we should be able to ideally understand any file and data structure that metadata is stored in. You need to test to make sure that your interpretation or your processing of that data is accurate, and obviously it needs to be shown to be reliable. So parsing the data then, if you have ever tried to parse a file that you are not familiar with, I'm sure most people have at some point, it's very difficult. You're kind of going blind, you open it up in hex, you start looking at it. It's a very arduous process. You can also make incorrect assumptions about offsets and about what various things mean. So just because something works this time doesn't mean it will work the next time you look at the same type of file. So it's often misunderstood, and this can often lead to an incorrect conclusion being drawn. So in terms of Spotlight itself, this is how it works. The core of the Spotlight system is the orange box there, the metadata server. So that's the software that actually runs the entire service. So every single file system event that takes place, FS events is a daemon that runs on Mac machines, which constantly monitors the file system for any changes. So all read, writes, deletes, modifications. When that happens, it updates the metadata server, say that there's a new file. So what that does is it then, if it pass it over to the Metadata Importer, which is what Apple call their tool for analyzing proprietary content. So Metadata Importer, pretty simply, for a JPEG photo, moving from the last talk, would automatically look for EXIF data and add that into the store. Okay? A Metadata Importer would also process a Word document. So it'll actually index the text in the Word document to make that text searchable. So you can use Spotlight to look within the documents on your machine, not just by file name. All of that stuff from Metadata Importer is sent back to the server, and all of these things are then stored inside the Spotlight databases, which is in the root of every storage media in a folder called Spotlight v100, and that's a dot directory, so that's hidden on Unix-based systems by default. Okay. Okay, so in terms of the events that trigger an update to the database, so FS events, again, is the daemon that runs, that monitors the file system for any changes. So for any of these events that are triggered, so creating a file, deleting a file, changing it, renaming it, modifying it, exchanging a file, so if you're actually just moving data between two files, creating a directory, you're changing the attributes, pretty much anything you do triggers an FS event, and that triggers an update to the metadata store. Okay? So the metadata importers that I mentioned, so these are a collection of tools that are able to consume proprietary file formats. So obviously, Apple, when they started off first, they knew all of their own file formats, so they created metadata importers for each of those. But over the years, they've added more and more of these importers, so now they can handle more files. So the thumbnail that you get, or the text search that you get, is far more powerful as the versions of macOS have increased. So there's a worker process then that is kicked off whenever there's a file system event, and then each importer will extract the metadata and a list of words, passing it back to the metadata store to store it back in. So the store itself then, this directory, if you look into it, so if you're on Mac, you can look into this on your own machine. It's in the root directory. So the stores are created on volumes, obviously, where the operating system has read-write permissions. So again, if you've ever shared data with somebody with a Mac and you're on the Windows machine and they fill your, it looks like they fill your USB key with lots of these dot files, the Spotlight files. Its presence on a disk indicates that that disk has been indexed by Spotlight at some point. There's a plist file on Mac which stores the location of all of the Spotlight stores that are being held on that local system. Okay, so this research is mainly focused on the metadata database. That's the thing that's interesting. So that's obviously where all of the metadata is stored, all of the updates, all of the index content is stored. So that is a proprietary database structure. Mac's documentation, Apple's documentation, does not provide any indication as to how that's formatted. So as part of the research, we kind of reverse engineered how it worked. So first of all, what's already out there then in terms of that? So I mentioned already the tool by 50 Forensics that's no longer available. There was no documentation to try and get you through the store.db file. Current methods of extracting it, so the current methods of interrogating Spotlight, use Spotlight itself. Okay, so the lookup service that I showed you the example of in the bash script, that's using the Spotlight tools to interrogate the database. There was no research out there that proves deleted records are recoverable, either directly or from unallocated space, and nothing out there describes the actual structure. Okay. So the approach to this work was first to try and figure out the structure of the database, to identify the records relating to each file, and trying to establish then what happens to deleted records. So are the records that are deleted recoverable from the Spotlight database? How long are they recoverable after the file has been deleted? What happens if the user intentionally destroys the Spotlight index? Can deleted versions of the database or database pages be recovered within unallocated space? Okay, so the experiments that I'm going to talk you through all follow this kind of same principle. So we use virtual machines. So we create virtual Mac OS installations, various versions of Mac OS X and Mac OS, the newer one. And the reason we use virtual machines was that it was fast and quick and convenient, but also it allowed us to easily create snapshots of the running machine and the versions of Spotlight after these particular events. We then populated the file system in the Spotlight database with known metadata. So we knew what we were putting, where we were putting it, and what we were doing. So we had a script to follow for the interactions with the disk. The reason we did that is because it obviously made it a lot easier to try and reverse engineer the database. So all of the entries associated with the actions that we performed, we knew that we had to try and find those in the database. We then created scripts that enabled the processing of the structures to try and automate it and to carve out the structures. So all of the pages, the headers, the records that are in that database file. We needed to process compressed content and encrypted content, and we need to identify all of the offsets and relative offsets for the records and flags. All of these scripts, as I mentioned, are on the GitHub. Then what we did was exploited that database structure that we figured out to be able to locate deleted records within the database, parse whatever information we could from them, and then we were able to search through, use that same technique to search through deleted databases in unallocated clusters. Okay, so we had 9 different experiments that we performed. So the first experiment was looking at the persistence of the metadata records within the store and unused space on the system. The second one looked at the persistence of the records on mounted volumes. The third, persistence of records on mounted volumes that were shared across 2 different operating systems, specifically Mac and Windows. Number 4, persistence of records when Spotlight indices are deleted using the appropriate command on the command line in Mac. Persistence of records when Spotlight indices were deleted via the GUI interface. Persistence of records when Spotlight indices are deleted using the terminal command and repopulated with a very large number of files. So you would think that would completely overwrite the content. Creation of metadata records for the purposes of reverse engineering the metadata store. You'll note that was experiment number 7 that we designed. So as I go through the experimentation, I'm skipping number 7 because everything else I'm showing you we learned during number 7. Number 8, we have the persistence of records when the operating system is upgraded, so both minor and major releases of Mac OS upgrades, and the persistence of the records then within the unused space. We use 10 casework forensic images. Okay, so what we discovered is there are 3 main types of database pages within the store.db files. So you have the header page, the map page, and the data page. They're each identifiable by the 4-byte signature. So you see the 4-byte signature there, which is always located at the beginning of the page. Okay. So the header page looks something like this. So this is an example. So in our experimentation, this page has always been 4096 bytes in length. Okay, that's not to say it always is, but in our experimentation, it always was. So you'll see here at the beginning of the file, you have the header string, which is 8TSD, which refers to the header page. You then have the page size, again, which has always been 4 kilobytes long. And then you have a variable length store.db file, because, of course, it depends where that database file is being stored, so it's of a variable length, and just that's a string to indicate where the DB file is, and that's terminated by a null. The second one then, the map page. So the map page is the database map, so it says where everything is on the disk. It describes each data page encountered within the database, I should say. The first 32 bytes provide the information regarding the page, and starting then at offset 32, which is the blue highlighted piece of the hex you're looking at. Each data page is described then using 16 bytes, and the first 4 bytes declare the size of each data page, and we don't actually know what the next 12 bytes are. We weren't able to figure that out. Store.db data page then. So these pages then contain different types of data described further in the paper, but we're really focusing on the metadata stuff for this talk. The header of the data pages are always identical, and the records for parsing the data pages were always found within the first 20 bytes of these pages. So the compression library, so you'll see here the content in red is junk. It looks like junk. It's compressed content. So Apple stores the metadata here using, in a compressed format using the zlib library. And the next slide, we have that decompressed. So you can see that it obviously contains useful information. So the metadata that's contained here and that we've highlighted and are described in detail in the paper includes the creation dates, modification dates, the file attributes, the owner, etc. The metadata that you might expect there to be there. It contains the file names and creation dates as well, which is useful later. So the interesting metadata out of this data page is, in particular, is the catalog node ID, which is in purple there at offset 4, and the parent catalog node ID, which is in pink there at offset 10. Okay. So it's similar here to a structure of a network database. So each record maintains a relationship with its parent and allows a hierarchical arrangement of records to be built. So the catalog node ID is used by HFS Plus to uniquely identify each file or folder on the system. An important feature of the catalog node ID is that they're not reused until they're exhausted, and then it cycles around. New files created on a HFS file system are given the next CNID, even if an earlier one has been made available because of a deletion. So it's a sequential issuing of it until they expire, and then it loops back around. Okay? So why is that important? We can use that to identify deleted files, so files that no longer exist within the catalog main index file within HFS Plus, and it allows us to recreate directory structures. So we know in this hierarchical structure, it is the mapping of the file system and the folders and directories. Okay. So our first experiment, we took, we added some files onto the system. We then deleted them. The store.db file, there's two versions of it. There's store.db and .store.db. So the dot file is obviously a hidden file again on Mac and Unix-based systems by default. We believe in our testing the dot file is actually the main database, and the store, the one without the dot, is the version that's the last known good one. So if anything goes wrong, it can revert back to that previous store, and then it can build the index again. This is what we've seen. The metadata records within the database persist for an amount of time after the corresponding file on the file system is deleted. If you do a large deletion event, so for example deleting a folder worth of files or whatever, entire database pages are dropped, and then if that's the case, they're not recoverable on the file system. So although Spotlight reported that indexing was complete, so Spotlight periodically again, it's monitoring the file system using FS events. So it indexes the content. If you plug in an external hard drive that has hundreds of thousands of files, it takes time to index that. Okay, so Spotlight will tell you the status that it's at for each new device that you plug in. So although Spotlight reported that the indexing was complete, not every file was actually indexed, because it takes several minutes for the files that are discovered to be passed to the metadata importers, to be passed back to the server, to be stored back out. Okay? So indexing is complete, it knows the files are there, but it hasn't yet processed getting all of the metadata out of those files. Okay. So after a short period of time then, the databases do catch up with all of the outstanding notifications from the metadata parsers. Okay. So each record, as I mentioned, is of variable size, and it sits back to back with the next record. So the data stored within these pages are compressed, and when the records are deleted, the remaining records show like a fluidity and collapse into the newly made space in the page. The consequence of this is that it overwrites any deleted records. So once a deleted record is removed from the database, they're no longer recoverable. There's a small asterisk there. If you did have access to the system and were able to move quickly enough, you could recover it, because if FS events, again, that's the thing that's monitoring the file system, if that's still trying to keep up with the events that are happening on the disk, if a large deletion event has taken place, for example, well, you have time there until FS event has a chance to catch up. But that only works if you're analyzing a live system. So it's possible that you could still recover the deleted metadata files if you look at the last good version, which is just the store.db file. So the last good configuration will still have those deleted records until that periodically updates. And if you examine the unallocated clusters, you can recover deleted pages from that database in those clusters, and you can still process them. So you can still find those deleted records in other places, they're just not in the live version, the .store.db. So in the second experiment, the databases were populated again. We added in files. We deleted a lot of files. So once we deleted from the store database, it's no longer recoverable. One noticeable exception that we encountered was on the FAT32 formatted volume. So every metadata record remained intact and is actually recoverable on a FAT32. So we didn't see this fluidity and this kind of collapsing of the record. It didn't matter that the files were deleted, and the last known good configuration, just the store.db file, that wasn't updated even after 30 minutes. The next experiment, we had two USB devices, one formatted exFAT, the other formatted FAT32. We moved them between Mac OS and Windows 10. So at snapshot 1, there was an expectation that the databases would contain 2753 records, but only about half of them were actually indexed. So that did skew the results, but the reason that is because the metadata importer is still working. Okay. Okay, the next experiment involved re-indexing the Spotlight metadata using different methods. So you can use the GUI, you can use the terminal commands. So when you re-index the metadata store, it resulted in the metadata store pages being deleted, and they are actually available for recovery from the file system directly. Each time the databases were deleted, the store databases were created again, as confirmed by a new catalog node ID being issued. In experiment 8, we were looking at the different major and minor releases and major releases of macOS. So deleted pages appeared within the unused space of the file system across upgrades. Examination of that file shows that the database itself is not deleted, but remained in the same location pre-upgrade and post-upgrade. A check of the physical location of the pages showed them to be in different locations from the site of the original databases. So it's suspected then that a copy of the metadata store is created when the system is undergoing a major update, and that copy then gets subsequently deleted, and during a minor update, that behavior does not take place. Okay, the last experiment then, we were looking to identify if deleted database files, or different database pages could be recovered from actual casework. So there was 14 different cases here. So unallocated records are recoverable from the unused space on file systems. Every database page was found to be the size of 16384. They were always found at a sector boundary on the disk. 5 of the examined images made use of a different version of the database, so store v1. So this is down to the, depends what version of Spotlight you had when you first used Mac, and if you, again, Mac users, you'll be familiar, when you buy a new Mac, magic things happen and everything comes over to your new Mac, so it pulls over all of those Spotlight directories with it. Although database pages are still recoverable, the records, you can't process them until, because the structure has changed. If you look at the last one here, this one I think is of particular interest, so the last case. This is an Apple hard disk, a hard disk that was originally shipped with an Apple machine, verified by the label and the versioning of the machine. And then it was subsequently used in Windows 10 as the primary storage device, as a secondary storage device formatted as NTFS. It was being used as on the Mac machine as storage as well. So it was NTFS formatted on the Mac machine. I tell a lie. It was HFS Plus to begin with on the Mac machine as it shipped with the Mac computer, and then it was in the Windows machine and was reformatted as NTFS. Now I'll continue my story. So, what was interesting is that we were able to recover, we're still able to recover the pages of the Spotlight database store, and we were able to recover records from the Mac machine. Over 250,000 records were still recoverable from the NTFS volume after it was reformatted. That's better, right? So, in summary then, the structure of the metadata store database was analysed and partially decoded. There was one thing that we couldn't figure out. Experiments were used to reveal that records persist for a period of time within one of the copies of the database. Once a record is deleted, it's no longer recoverable from within the database, but could still be recovered from a copy or from unallocated clusters due to that fluidity. Deleted pages from the database are recoverable from unused space on the file system. If the operating system undergoes a major update, it appears that a copy of the metadata store is created before subsequently being deleted. Database pages can be recovered from the unused space on the file system, and if the Spotlight index is reset, re-indexed, or recreated, the whole metadata store is deleted, and then you can get those database pages still from the unused space on that file system. So if you're interested in learning more, obviously your first protocol will be our paper that's just published in this conference. But your second protocol, completely coincidentally and in parallel and without any communication, there was a paper published just last month in Digital Investigation called Investigating Spotlight Internals to Extract Metadata. Okay. So this was by Yogesh Khatri. I hope I'm pronouncing that correctly. So what's interesting is that our scripts that we're providing are all Bash-based scripts. Yogesh did it all in Python. Again, it's open on his GitHub. You'll access the GitHub links there. The difference between our research and this published research is that we were able to, and we were focused, and we were able to recover deleted records. So once a file was gone, we were able to cover that information from the metadata store. So both approaches were trying to reverse engineer the proprietary store.db file and the associated pages, and that's what's highlighted in that Digital Investigation paper that was just published as well. Okay, so that's all I have. I'll try to take any questions you have. There's one at the front here, I don't know.
So my question is now, have you done an experiment on APFS?
Yes, is the answer. So we don't have results yet. So APFS is a game changer in terms of how this stuff is conducted. In our experimentation, it makes like recovering the deleted pages from the unallocated clusters not viable, right? So, but we are currently looking at this, and this research is continuing, and certainly APFS is on our list, but we don't have such results yet. Okay, everyone else is happy, thank you.